All right. Today we're going to tackle a really cool and, honestly, fundamental idea in statistics. How can we take a tiny little sample, a small group of people, and use it to make a really powerful, educated guess about an entire population? Let's get into it.
I mean, think about it. You see this all the time, right? Political polls, market research, they talk to maybe 1,000 people and then confidently make claims about millions. How in the world do they do that? Well, that's the exact question we're going to answer today.
Okay, so where do we even begin? Well, the most logical place to start is with our single best guess, the simplest, most direct answer we can pull from the data we have. And in statistics, we have a name for that, the point estimate.
So, think of it this way. The point estimate is just our best shot. It's our starting point. If we surveyed 100 people and 42 of them said yes to something, our most logical guess for the whole population isn't going to be 50% or 30%. No, it's the 42% we actually saw with our own eyes.
And this is the beautifully simple formula we use to get that guess. We call it p-hat. That little symbol over the p looks like a hat, right? And it's just the number of people who said yes divided by the total number of people we asked. This p-hat is our best point estimate for the real proportion of the whole population.
And just to make sure we're all on the same page, let's break that down. X is just the number of times we got the result we were looking for. In stats, we call these successes. And N is our total sample size. That's it, just those two pieces.
Now, a single number guess is a great start, but here's the thing. It's almost guaranteed to be at least a little bit off, right? The real world is messy. So what we really need is to build a kind of safety net around our best guess, a range of values that's probably correct. And that's where the confidence interval comes into play.
A confidence interval does exactly what it sounds like. It takes our point estimate, our best guess, and builds that safety net around it. It gives us a lower boundary and an upper boundary, and we can say with a certain level of confidence that the real, true value for the entire population is hiding somewhere in that range. It's like an estimate with humility built right in.
But hold on. We can't just slap these intervals on any old data. We have to do a few quality checks first to make sure our math is actually valid. The data has to be random, the sample can't be too huge compared to the whole population, and this little calculation here has to be at least 10. Think of these as the rules of the road. You gotta follow them to get a reliable result.
Now, this exact phrasing is so important. When we interpret a confidence interval, we're not saying there's a 95% chance the true value is in our specific interval. What we're really saying is that we are 95% confident in the method we used. If we did this whole process 100 times, we'd expect the true value to be captured inside our calculated interval about 95 of those times. It's a subtle but crucial difference.
So, how wide should the safety net be? Is it big? Is it small? Well, that's determined by something we call the margin of error.
The margin of error, we just call it E. This is that plus or minus number you always hear on the news when they talk about polls. It's basically our wiggle room. It tells us how much uncertainty we have wrapped around our point estimate. Naturally, a smaller margin of error means we're being more precise.
The formula to calculate it looks a little busy, but it combines three key things: our sample proportion, p-hat, our sample size, n, and this new value, z, called a critical value. That z-value is all about how confident we want to be. If you want to be more confident, you need a bigger z-value, which gives you a wider, safer margin of error.
And once you have your margin of error, building the interval itself is the easiest part. You literally just take your point estimate, p-hat, and you subtract the margin of error to get the low end, and you add it to get the high end. That's the whole shebang.
Okay, so everything we've talked about so far is for when you already have the data. But what if you're designing a new study from scratch? How do you know how many people you need to survey to get the results you want? This is where determining your sample size comes in, and it's maybe one of the most useful skills in all of statistics.
We've got two main ways to do this. If you have a pretty good idea of what the answer might be, maybe from a past study, you can use that prior estimate in the formula on the left. But what if you're flying completely blind? No problem. You use the formula on the right. That 0.25 is our conservative worst-case scenario guess. It guarantees your sample will be big enough no matter what. And listen up, because this is a rule you absolutely cannot forget. When you calculate your sample size, n, you're going to get a decimal. It's unavoidable. But since you can't survey half a person, you must, and I mean always, round up to the next whole number. Even if the calculator says 150.1, you need 151 people. No exceptions.
All right, enough theory. Let's get our hands dirty and see how all these pieces, the point estimate, the margin of error, the whole interval, actually work together in a real example.
This is where it all clicks. Okay, let's pretend we did a survey and found that 42 people had the trait we were looking for. So our X is 42.
And let's say we asked a total of 100 people. That makes our sample size n an even 100.
Okay, first things first, we got to do our due diligence and check the conditions. We'll assume the survey was random and that our 100 people are just a small fraction of the total population. Then we do the math check. 100 times 0.42 times 0.58. That gives us 24.36. That's way bigger than 10, so we get the green light. We're good to go.
Now we just follow the recipe. Step 1, calculate our best guess, p-hat. That's just 42 divided by 100, which is 0.42. Easy enough. Step 2, we plug everything into our margin of error formula for 95% confidence, and we get about 0.0967. And the final step is to just add and subtract that from our best guess.
And boom, there it is, our final confidence interval. It runs from about 0.3233 up to 0.5167.
So we can finally make our statement. Using that precise language, we can say, we are 95% confident that the true proportion for the entire population is somewhere between about 32.3% and 51.7%. See what we did? We took a tiny sample of 100 people and created this powerful, meaningful estimate about the whole group. Pretty cool, huh?
And that leaves us with one final thing to think about. I mean, being more confident always sounds better, right? So why don't researchers just use 99% or even 99.9% confidence all the time? What do you think you have to give up to get that extra bit of certainty? That's the big trade-off between confidence and precision that sits at the very heart of statistics.